Welcome. Today we're going to talk about fields, but not just any field, not one with grass. We're going to talk about electric fields. But to get started, let's first look at something you're a little bit more familiar with. This is Earth, if you couldn't tell. Earth is an object that has a mass, and anything with mass has a gravitational field associated with it. You can think of a field almost like an AM radio station where you have this beacon, right? And it just sends out messages. And the closer you are, the louder it is. So if you're right here, then you might get a really strong signal. But if you're out here, it'll be a weaker signal. So here it's really strong. Here it's not so much. In fact, the signal drops off at 1 over r squared. And this is true for lots of fields, not just the gravitational field from Earth. You'll see later that it's also true for electric fields. So back to Earth. No matter where you go around the Earth, near, far, on it, you experience the effects of the gravitational field. We encounter it as this acceleration due to gravity that pulls all things into it. That's because no matter where you are in the universe, there's always this piece that says, hey, Earth's over here, it has mass, and any other objects with mass are attracted to it. And again, it's important to point out that the closer you are, the stronger that attraction. So the further you go out, the weaker. Remember, it goes as 1 over r squared. So enough about Earth. It's time to talk about the electric field. But to do that, I'm going to clear the screen. Alright, let's keep going. Now that I've gotten rid of the Earth, let's focus on, right here, we'll have a positive charge. So this positive charge, unlike a mass that just has an attractive force, this positive charge will interact with other charges, positive or negative, and either attract or repulse. A simple thing to remember is that these like charges will repel one another. So this one would push this one away, this one would push this one away. Whereas if you have opposite charges, they'll experience a mutual attraction. So, let me clear everything again, and now we'll keep going. Back to our positive charge. A positive charge like this just sits there like a mass, and it has an electric field as well, and it tells all the protons around it, hey, go away, I'm already here. And it tells all the electrons, hey, I'm here, you should come over here. And it does this much the same way as a gravitational field does on Earth, except with the electric field, it's repulsive and attractive, depending on the other particles. So, let me make this part clear because it's really important we are all on the same page. When we draw an electric field, regardless of whether it's for a positive particle like this one, or a negative particle, which we'll draw in a moment, we're going to draw the field in the way that a positive particle would behave when placed in that field. For instance, with this positive source charge here, any other positive charges placed near it would experience an electric field that pushes it away. That gets weaker as 1 over r squared, as fields do. Like so, all directions. Strong up close, weaker as you get further out. So, if that's a field for a positive charge, now let's just make one little change. Now let's have an or an electron or a negative charge here at the beginning. A positive charge will behave differently now. It will be attracted. That attraction will fade away the further you go out. It gets weaker. Notice most of the field lines are exactly the same, just the direction has changed. And again, this is to illustrate the point that a positive charge is going to be attracted to a negative charge, because we always draw how a positive charge would behave when placed in the field when we're trying to illustrate field lines. Now, one charge is fine enough, but what we really want to look at is multiple charges and the field they generate. So let's get rid of this electron and let's just put some basic charges out and see what it kind of looks like. So I'm going to switch to the symbol Q here, Q minus, Q plus. We're going to look at how a positive charge would behave when placed in proximity to these two charges. Well, if we took a charge and we put it right here in the center, it would experience a repulsion from the positive and an attraction from the negative. So overall, it's going to move that way. In fact, anywhere along here that you put a particle, the field's going to go that way. If you put a particle here, again, remember it's always a positive particle, it's going to feel this attractive force from the negative one, and it'll feel slight repulsion from the positive. It's further away, so the field won't be as great. If you put one here, it'll experience a great repulsion from the positive and slight attraction from the negative. All in all, you could go around and do this at different points, but overall what you'll begin to see is a field generate like this. Again, each one of these arrows represents the direction a positive charge would move. So you can use this kind of notation in drawing fields for just about any arrangement. In fact, what I'd like you to do next is try one out yourself. Here we have two negative charges. Just for fun, but also bring it to class, I want you to look at how a positive charge right here would behave. Bring that to class with you next time we meet and we'll talk about it. That's the end of this video. Be sure to check out the next one so you can see the equation for the electric field, because we'll be making use of that in class as well.